So good morning class. For our lesson for today is about iterated integrals. And our learning objectives at the end of the lesson, the student must be able to first define iterated integral and second is to evaluate iterated integral over a rectangular region. What is an iterated integral? An iterated integral occurs when we want to integrate a multivariable function such as f of x, y, and f of x, y, and z. Through iterated integrals, we can evaluate this function by taking the integrals of the function consecutively and with respect to one variable each time. So suppose that f of xy is a continuous function within its rectangular domain. R is equals to 8b times cd. By Fubini's theorem, we can define the double integral of f of xy with respect to dx and dy as the iterated integral shown below. So the number of single integrals represent the number of times we'll integrate the given function. So this means that for double integral, we'll integrate this function twice in a row. So the integral of c to d with a function of xy dy, this is the function in terms of our x. And the integral of a to b with a function xy dx is a function in terms of y. So the two forms highlight the importance of iterated integrals. We calculate them with respect to one variable first by treating the other variables as a constant. We repeat the process until we have completely evaluated iterated integral that were given. How to calculate iterated integral? So we can calculate iterated integrals by integrating with respect to one variable first, just like partial derivatives. We start with the innermost layer and partially integrate the function with respect to the innermost variable. So this is the process of how to evaluate iterated integrals. So we have the integral of c to d and our interintegral a to b with the function x, y, dx, dy. So first, we will integrate the function with respect to x, first treating y as a constant, and then you will be evaluate the resulting expression from x is equals to e to x is equals to b. And then on the other hand, integrate the function with respect to y, treating the rest as constant, and then evaluate the expression at the limits from y is equals to c to y is equals to d. On the other hand, we will be evaluating the integral of a to b and then the interintegral of c to d with the function x, y, dy, dx. So first, we will integrate the functions with respect to y first, treating x as a constant, and then evaluate the resulting expression from y is equals to c to y is equals to d. And then integrate the function with respect to x, treating the rest as constant, and then evaluate the expression at the limits from x is equals to e to x is equals to b. So we will evaluate iterated integral over a rectangular region with a function f of xy is equals to 2xy minus 3y squared, and we need to find the integrated integral over the region -1 to 1 by -2 to 2. And these coordinates here define a rectangular region. So when we're talking about integrated integrals, we are finding the area of a rectangular region defined by the coordinates here in our R. So looking at R here, keep in mind that R is basically x times y. Then this first set of coordinates is always your x coordinates and this second is your y coordinates. So it doesn't really matter whether we integrate with respect to x first or y first. We can do it either way, but we usually like to do is x first unless doing so. So now we will do the coordinate here for y first. So the integral of -2 to 2. Then we do our interintegral, which is the coordinate of x. Integral of -1 to 1. And then we put our function inside. So our function, this is our function, 2xy minus 3y squared dx dy. So take note that this outer, the integral of negative 2 to 2, corresponds to our y. And this inside, the integral of negative 1 to 1, corresponds to our x. So working from the inside, this one, the integral of negative 1 to 1 to xy minus 3y squared dx, and we're integrating with respect to x first, and we're holding y as constant. So we just copy the y, negative 2 to 2, and then our function 2x, since this have the invisible 1 plus 1, it will become squared, times our constant y minus 3xy squared times the integral of our x, negative 1 to 1 dy. So after this, we will simplify. So the integral of negative 2 to 2, this will have a over 2. Since our exponent is 2, then we will put 2 here in our denominator. So 2 divided by 2 will become 1, or we just can cancel it out, and then we will have x squared y minus 3xy squared times the x is negative 1 to 1. So now we will be substituting the value of x. So negative 2 to 2, 1 squared, and our constant y minus 3 times our x, 1 times y squared minus our x here is negative 1 squared y minus 3 times negative 1 y squared dy. Then simplify. So the integral of negative 2 to 2. So 1 squared is 1 times y. So it will become y minus negative 3 times 1 y squared will become 3y squared minus negative 1 squared is 1 times y, become y, and negative 3 times negative 1 will become positive 3 y squared dy. So since our middle or our sign is negative, therefore we'll put negative 3 y squared dy. So y minus y will go away, or we will just cancel it out. So negative 3y squared minus 3y squared dy is equals to the integral of negative 2 to 2 negative 6y squared over, so since we will now be looking for our y, we'll add plus 1, so it will become 3 dy. So negative 6y cubed over 3. So since negative 6 divided by 3 is negative 2 y cubed multiplied by our y coordinates, which is the integral of negative 2 to 2. And now we will be substituting the value of y. So negative 2 times 2 cube minus negative 2 times negative 2 cube. So negative 2 times 2 cube is 8 minus negative 2 times negative 2 cube is negative 8. So negative 2 times 8 is negative 16 minus negative 2 times negative 8 is negative 16. And negative 16 minus negative 16 is equals to negative 32. So this is now our answer in evaluating integrated integral over a rectangular region with a function f of xy is equals to 2xy minus 3y squared over a rectangular region of negative 1 to 1 by negative 2 to 2.